Mobility Days. Before I introduce our speakers this afternoon, I'd just quickly like to go through some general housekeeping rules for the webinar. I think most people will be familiar now with how the setup works, but on the side of your screen, you'll have various tabs. One of those is the chat function. This will be open throughout the session. Please feel free to interact with the other attendees, or if you have any technical issues, let us know, and a member of the team will be able to resolve that for you. The Q&A, please ask questions throughout the session. We have around half an hour reserved after the 3 sections of this presentation to go through all of those questions with our speakers. The session today, we have booked in for roughly 90 minutes, and as I say, around 20 to 30 minutes at the end reserved for Q&A. So without further ado, I'd like to now introduce our fantastic speakers who will be discussing closing the value chain in electromobility. So I'm joined today by Dr. Jörg Zimmermann, the Head of Department for Energy Materials at Fraunhofer IWKS, Jürgen Gassmann, Head of Department for Magnetic Materials at Fraunhofer IWKS, and Dr. Andreas Stegmüller, Digitalization of Resources for Fraunhofer IWKS. Welcome to all of you. Thank you for joining us. And I'd like to hand over to Jürgen now to kick us off with the presentation.
Thank you, Liam, for the kind introduction and for the possibility to speak in this nice session. I'd like to welcome you, all of you. I'd like to present our results in terms of the value chain for electromobility. Just to give you an idea where we come from, we are from Fraunhofer. Fraunhofer is the biggest society for applied research in Germany. Fraunhofer is located all over Germany. We are in Alzenau and Hanau. Hanau, right in the central of Germany. Hanau is Hessen, Alzenau is Bavaria. So we have this specialty to have like 2 institute buildings. However, Fraunhofer Society is about 74 individual institutes all over Germany, and about 28,000 people are working here. We have a turnover in 2019 of roughly 2 billion euro. So that's the whole society. We are an institute dealing with resources and criticality. In our department, in our institute, we have 4 departments. One department is dedicated to bioplastics, bioeconomy, new materials from bio systems where from biogenic raw materials were generated. We have a material flow department where Andreas Stegmüller is located. Here we do life cycle assessment studies, life cycle costing, we do criticality analysis, and we do modeling of flows, material flows. Energy materials department, where Jörg Zimmermann is from. Here we are dealing with recycling of lithium-ion batteries, for instance, but also other energy-related materials. We are also dealing with hydrogen, for instance, or with recycling of solar cells. And last but not least, the magnetic materials department, where I work in. We basically do research on permanent magnets, find new ways to synthesize magnets without critical elements, or to recycle them. Just a small overview, what we like to do is we like to interact the performance of functional materials with the sustainability, meaning that the physical performance don't need to be always the highest if the material is very sustainable. So for that, we do different kind of research. We try to work on low cost and abundant materials. We try to implement a circular economy for other kind of functional materials like batteries or magnets. And to show you just some impressions, we prepared a small clip from our institute buildings.
The electromobility is one of the cornerstones of the mobility and energy transition. In order to increase sustainability, researchers at Fraunhofer IWKS are working on more efficient recycling processes. At our technology site in Hanau, research focuses on the assembly and recycling of batteries as well as magnetic materials and their recycling. In the area behind me, we are currently developing the Center for Disassembly and Recycling for E-Mobility, in short ZTRE. We are working on disassembling and recycling components of electric mobility, such as batteries, fuel cells, motors, as well as power electronics. To do so, we have several modular units. For example, you can see behind me the water jet cutter used to cut open batteries and motors. On the other side, you can see a 4-shaft shredder for fragmenting. To recycle lithium-ion batteries, we are using a special technology called electrohydraulic fragmentation. The batteries are placed in a reactor filled with water. Then shock waves generated by high voltage propagate through the water and hit the material. The fragmentation occurs at natural boundaries of the material, making it easier to sort the material afterwards. As a result, we regain various material fractions such as the separative foil, aluminium, copper, as well as the active material. We are now coming to the area that is dedicated to magnet recycling. We are investigating different options to recycle end-of-life magnets and make them available for new applications. Furthermore, we are working on the substitution of critical elements in permanent magnets. In the melt area of the technical plant 2, we have several options to develop metallic melts containing rare earth elements. The cooling speed can be increased up to 10 to the power of 6 Kelvin, which
I think there was a half-minute misses, but it's okay. Basically, I can show you the details now. So we have now the 3 sessions with magnets, with batteries, and with the multi-property model. So what are we doing in the magnetic materials department? Like I said, recycling is a key challenge for us because the material is just valuable, and at the moment it's not really industrial recycled in Europe. The second thing we try to do is to substitute critical materials. We are talking about rare earths, we are talking about heavy rare earths. We develop new technologies for substituting them in magnets. And last but not least, we are also producing magnets with less critical light rare earths like lanthanum and cerium. However, I won't talk about this issue today. I will focus on the recycling and a bit on the substitution part. So in the video, you saw our new institute building. So we moved basically our equipment from one side to the other since we are a new institute. However, in the last 5 years, we installed a small lab factory for magnet production in Hanau. We try to work with sintered magnets, with hot deformed magnets and polymer bonded magnets. All these devices can be used in e-mobility, in wind energy, or in small motors. We try to come up with new recycling technologies above lab scale. So we're working in the batch scale of 10 to 50 kg. For that, of course, we have also the analytics because we need to understand the magnetism behind our processes. And if there is something needed, we can measure magnetic properties in all ranges of temperature and fields. We can measure the microstructure, which is important for us, and we can also measure in an atom on an atomic level the stoichiometry, which is also important. I will come to that just later. So why are we doing that? At the moment, we are knowing that there is a global warming. We have a CO2 emission which needs to be decreased for meeting the goals of the Paris Declaration. And depending on which kind of model you are looking on, in the mobility sector, it needs to be a change. So the change need to be the implementation of electric cars in the worldwide stock. So here on the model you see in the year we are pretty much at the beginning. However, the demand for electric vehicles will increase in the next decade. And for these devices, you basically need other kind of materials. For a motor, for instance, you need up to 1.5 to 2.5 kg per motor of neodymium iron boron magnet. You also need possibilities to store the energy, for instance, in batteries, where you can have something like 300 to 500 kilogram independence of the range. You can also store it in hydrogen. However, you won't use natural fuel anymore. When you think about the magnets, you see that the demand for neodymium iron boron magnet, which is the most dominant magnet on the market, is basically driven in the next years by the drivetrain in electric vehicles. And for these magnets, you need elements like light rare earths, heavy rare earths, which may become critical, and a supply can be a problem. The same is also true for the material for batteries, lithium, cobalt, and also for the power electronics, copper. Jörg Zimmermann will talk about that in the second session. If you have a very actual view on supply risks for the European Union, you can have a look in this foresight report from last year's. And you see in the report, the materials with the highest supply risk by far were the rare earths. These materials are used in wind energy, in wind turbines, and basically in motors for electric drives. If you have a look on the current price for these metals, the light rare earth neodymium, the heavy rare earths dysprosium and terbium for the last 6 months, you see a drastic price increase. In the year 2011, there was some price anomaly. Already the price was going back again to a normal level. However, in the last 6 months, prices increased again and doubled almost their values. So the supply risk can be a problem when you deal with neodymium iron boron magnets, with the demand which is coming to us. Another thing is also the ecological footprint of this material. So this material is basically mined in China and in Australia with about a share of 80 to 20. The mining is not really a nice business for the environment in this case. About 90% of the energy is consumed by producing a magnet, is consumed in the very first states of mining, extraction, metal fabrication. About 50% of the losses is also there. And the rare earth elements are always coming, most of the times they are coming with radioactive elements, which you need to deal with when you extract these materials. So it's just ecologically feasible when you produce magnets out of these elements for a green technology like electric cars, that you use also the circular economy, because you can get rid of a whole bunch of energy needed for the primary mining. You can decrease the total tailings and the amount of radioactive elements exposed. What you need is a collection system for scrap magnets. You need to disassemble applications. You need to recondition scrap magnets, and then you can produce new magnets out of that. For different kind of applications, I will show you some possibilities. Independence of the material you are using, different recycling routes may be feasible. When you think about very small magnets in phones or in other electric device, just a few grams, then an elemental recycling may be favorable. Elemental recycling in this case means you take the neodymium iron boron magnet and you dissolve it into pure neodymium, pure iron and pure boron. And then you can produce whatever you want out of these elements. However, you also need there a lot of energy, a lot of chemicals. When you have, for instance, magnets from wind power, for instance, or also from electric cars where you have a huge amount of magnet in the motor, you can stay within the system of the magnet, meaning you can produce a neodymium iron boron magnet with the same grade out of a neodymium iron boron magnet. And this is functional recycling. And that's something we are looking on at Fraunhofer. When you think about e-mobility, I think there are two strategies in terms of permanent magnet recycling. One is use recycled magnets for motors in e-mobility. The scrap magnets for the recycled magnets can come from every kind of application, of course, also from e-mobility. However, there is at the moment no scrap in huge amount from e-mobility. The second thing is that you really use the scrap from the e-mobility in a small amount, and in the perspective of 10 years, you have a huger amount coming back from the e-mobility, recycle that maybe for some different applications. So I will talk first about the first one, so use in electromobility. For doing so, you need to reach magnets with a certain property, and you can do that with a powder metallurgical process. The process is not really changing so much from natural producing magnets from the elements. However, you don't start with elements, you start with a scrap magnet, which is called here primary magnet. Then you powderize the material. You can use, for instance, hydrogen for that. You have to mill the material to a very fine powder. Here you can also blend the material. So the first possibility is to change composition and also change the properties of the product. You can press it and sinter it at higher temperature. And last but not least, you cut and grind it to the specification you need for your device. And if magnetic properties are not high enough, you can still do some post-processing processes, and you can also, of course, coat the material so that it's also resistive against corrosion. I will highlight some details about the hydrogen decrypitation process, basically. So when you see, this is a video cut it into 6 pictures. Basically, what you see is you have a rare earth permanent magnet, neodymium iron boron, in a hydrogen atmosphere, and you just have to wait. The hydrogen will diffuse into the crystal structure of the magnet. It will form some stresses, and these stresses will powderize the magnet. And this powder you can use for further processing the recycling route. In this case, we did it, for instance, with a rotor with a surface mount magnets. You see it on the left-hand side. In this case, it was magnetized. It wasn't. It had some glue, but it was basically fixed with the steel plates, with the steel rings. And after hydrogen decrypitation, you can separate the powder from neodymium iron boron from your motor, because the hydrogen in these conditions just affect the magnet and not the steel part. So you have some powder, and this powder, like I showed you before, you can further process, and then you get a sintered magnet. When you make a magnet out of that, you have different kind of possibilities. So basically, our goal is to meet the specification of the customer, and a magnet is defined by 3 important dimensions. So one is remanence, is on the y-axis. You want to have a high remanence, the highest remanence possible, basically, because then you can have a huge magnetic moment. On the x-axis, the coercivity, you want also to have a high coercivity because it will avoid the magnet from demagnetization, which can happen at higher temperature. When you have some eddy current heat up, for instance, you can have higher temperatures. The motor is operating at temperatures above 100 degrees C. you can have some demagnetization and the motor can't be used anymore. Therefore, you want to have a high coercivity. And all of that you can tune by the recycling process. You can work with the chemical composition of the scrap magnet. You can work with the microstructure of the recycled magnet. You can put some additives inside. In this case, it is shown for dysprosium and terbium that you can have a coercivity increase about 500 kiloamps per meter without decreasing resonance when you add about 2-8% terbium inside. Terbium, however, is a pretty expensive element, like I showed you before. But what I like to stress here is basically you can achieve the specification which you also can achieve from when you produce a magnet from elements. When you go more into detail, in this case, we combine different kind of methods. We use grain boundary diffusion, which is a method where you can concentrate heavy rare earths on the cores. In the central, you see an SEM image. You see that in the middle of the cores, the heavy rare earth content is pretty low, indicated with the dark color. And at the core shell, the heavy rare earth content is high, indicated with the light color, meaning we just need the dysprosium in this case. You can see on the right-hand side, measured with atom probe, that the dysprosium content is just on the grain boundary. So on the grain boundary, demagnetization effects will occur. Therefore, we have to harden, magnetically harden this phase. And this can be done. The process, of course, is known from primary material production for magnets. However, it can also be used for recycling technologies. And it is shown here nicely that by combining different kinds of grain boundary modification, grain boundary diffusion processes, you can tailor the magnetic properties to meet the demand of the specification. So scrap magnets from electric cars as a source. This is something which starts now, but will be more demanding in the near future. So if you have a look on an electric car, you already have a lot of motors inside, and some of them are using magnets. Some of them are using ferrites since they are quite cheap and they are not size related. Some of them need to use rare earth magnets like neodymium iron boron or samarium cobalt. On the right-hand side, you can see that the demand in the year 2019 was a production of magnets, the use of neodymium iron boron magnets in which kind of device. About 9% already were used in the drivetrain of a car for fully electric vehicles or for hybrid electric vehicles. And we are interested, of course, in the traction motor. For our process, it is very important that the magnets are separated from the soft magnetic material and the rotor itself, the steel components, because most of the material is iron, of course. Also in the magnet, about 70% is iron. So nowadays, these devices were recycled together with the main element, iron. And the pretty precious rare earths, they were just lost because they get oxidized and they can't be used anymore. So the separation is key for us. Here we are checking and doing research how to get out the magnets as automated as possible. We are starting to using robotics for that. And also the demagnetization is important. In which state the magnet is demagnetized? Do I have to heat up the whole device? Can I just heat up the magnets? How can I deal with the polymers inside? This material is most of the time is some glue. Some of the magnets are also clamped, and so different kind of devices. All the stuff we are checking to extracting the magnets on the most economical way. And for doing so, we have a partner also who uses these magnets. So we as Fraunhofer, we're doing research and we are selling technology to the industry. And in this case, we work with a partner who like to implement the recycling of magnets by a rapid solidification technique. So in this case, on the left-hand side, you see the melt spinning technique where we have this really high solidification times. The cooling is within tenths of seconds, and you get the material which is nanocrystalline. This material you can use for fully dense hot-deformed magnets, for instance. In Europe, more commonly, you produce polymer bonded magnets out of that. These magnets can be used in other kind of small small motors where you have high RPM, where you need small eddy currents, for instance. And on the right-hand side, I just show you some comparison of one of the grades which is already on the market available from a company, and one of the recycled products we produce in this project so far. So we are doing it on a smaller scale. However, the company tries to implement it in the second year, in the autumn of next year, so that it will be industrialized and that the first recycled flakes for magnet production from Germany can be delivered. So that's something pretty exciting for us, since we have there a huge partner bringing that into the market. Last but not least, I have two more slides because we are also looking for partners in terms of other kind of projects. So the end-of-line recycling project for traction motors, drivetrain motors, I already mentioned 2 slides ago, but I think here is still some work to be done. We need the partners who are working with this kind of motors, who are interested in dismantling them, to give the magnets to a recycling chain, to have a circular economy for the rare earth permanent magnets. Just to give you an idea, our impression is that we can increase the value of the end-of-life device of the motor with such a project. We also can increase the sustainability, since the magnet is not dumped, it's recycled and used for other kind of product. When you buy magnets, sintered magnets nowadays, independent of performance, geometry and supplier, you will pay something like 40 to 70 euro per kilogram of neodymium iron boron magnet. At the end of life, you will get nowadays something, the market is not really there yet, but you will get something like 5 to 20 euro per kilogram for scrap magnets, also dependent on the composition. And if you recycle it with a steel, and like I showed before, 70% of the magnet is iron, you will get 25 cents for the kilogram. So I think there is just a value which can be gained, and in terms of sustainability, it is feasible to do. And we see a possibility for now, because the motors are now produced, they are in testing phase, and then they might be dumped. So this dismantling efforts can already be done. But in the future, this huge demand, which I showed you before, this can be also tackled in the year 2028 or 30, when the first electric vehicles really can come back. So it's a long-term perspective. And the second project we are trying to do with our colleagues from Fraunhofer FIT, one of the other 74 institutes, they are specialists in digital methods and the blockchain. And we try to implement digital methods for the circular economy. When you think about magnets, it is important that you collect this device at the end of life. You need to know how you can dismantle the product. Therefore, you need to have some knowledge on product design. And if you are a company, trying to doing this recycling, you need a safety of supply. And all of that you can tackle with the blockchain. And we want to do a public funded project where we use, where we need also partner from research and development and also from industry. And we think that we can show for an electric motor, for instance, for the devices within an electric motors, that we can tackle that with the blockchain. It can be a digital market to trade materials like copper, like steel, but also like scrap permanent magnets. It is also possible to store information from the design that a recycler can buy it just in time when he needs it to dismantle the device. Also, the safety of information is there. And to combine that, we'd like to show that with a product which is an electric motor. So if you're interested, just give me a call. We are keen to talk about that. So my take-home message is short. Rare earth permanent magnets will play a key role in decarbonization of the mobility sector in near future. But we need different kind of materials for that, and therefore we should think about recycling these materials, because the mining is not very sustainable. And in terms of electromobility, you can be a user of recycled magnets, or you can be a source for recycled magnets for new products. So I'm looking forward to the Q&A session at the end, and I will hand over now the microphone to Jörg Zimmermann, who will introduce you to our tasks in the battery recycling.
Yes, thank you very much, and thank you for the opportunity to speak here, and welcome from my side. I'm going to talk about the lithium-ion battery recycling, but first let me draw your attention to the Center of Disassembly and Recycling for the E-Mobility. This is a funded center or funded project by the Hessen State Ministry for Higher Education, Research and Arts. And it started last year in April. And here we focus on the recycling and disassembly of the components like battery, the motor, and of course, if it's available, also the fuel cell. In this session, I just want to talk about the recycling of batteries. But first, let me show you some slides for a better understanding of the challenges that battery recycling provides. You can see here that not all the batteries are the same. This slide shows 3 battery systems, and the differences are obvious. Differences in shape, dimensions, and constructions. So you see, we have a huge diversity on the system level, but when we go a step further to the cell level, the situation is almost similar. We have 3 different types of battery cells. The pouch cells on the left side, and in the middle you can see the prismatic cells, and on the right side we have the round or cylindrical cells. And each type in turn can be found in different dimensions. So also on the cell level we have a huge diversity, and if we go a step further to the materials level, in principle it's the same. Also here we have huge diversity. We have different kind of materials, especially the cathode material. You can see we have different kind of compounds, and also the prominent materials NMC, which is nickel, manganese and cobalt oxide together with lithium. We have different relations in the compounds. So you see, it's not easy, and we have this huge diversity on the different levels. I found a book from Tobias Elbert, and if you find these 2 sentences here, vehicle design has to strike compromises between crash safety center of gravity and space optimization, which must be balanced against serviceability. And the next sentence, these conflicting design objectives often result in designs that are not optimized for recyclability and that can be time consuming to disassemble manually. So these two sentences say very clear that it's not easy to have a recycling process for all the batteries. It's not easy to have an automation for batteries and battery cells. So we have to think in a different way. And of course, there's another challenge. The challenge of diversity is one thing, but the other thing is safe handling, since battery is a source of danger in different ways, as shown here with the hazard symbols. I think I don't have to go into detail. You can all imagine that the batteries are not easy to handle. And taking these challenges into account, we come to the conclusion a disassembly and recycling must be safe, robust, efficient, and sustainable. Currently, different process routes are in use. The pyrometallurgical way, which is shown on the left side, where cells or modules are melted. The output is a slag and an alloy of the wanted metals. Or we can go the other way. The other way is the more prominent at the moment. This is mechanical shredding, and you can do this mechanical shredding assisted by cryogenic conditions, for example, or under nitrogen atmosphere. Or in other cases, it's just combined with a thermal pretreatment. And both are for safety issues. And we have a different kind of way, so it's an alternative to the mechanical way, I would say. And this is the hydromechanical process. You can see here in the middle, which is underlined blue, this is the core of the hydromechanical process. In principle, we have on the left side a water cutting system with which we can cut the battery system, and we can also pre-cut the cells for a further treatment. The second is a shredding under water or under water shower, where we can open the cells, but just open the cells. It's not for shredding down to small grains. It's just to open the system, to open the battery system, and also to open the cells for the next step. The next step in the middle here is the electrohydraulic fragmentation. You have seen that in the video before, but I will show you a slide to explain that again. And after this treatment, we have different fractions, which we can sort by a very simple way, just by skimming and sieving. So first we take off the plastic by skimming, and after that we make a sieving process to get the black mass and the metals separated from another. And of course, as in all cases, for the pyrometallurgical way and also for the pure mechanical way, at the end, we need a hydrometallurgical pass to get the elements back. Now, first thing is to open the system. In this case, we used for our experiments a Pedelec battery, not a complete big system for cars, but in this case a Pedelec system. And the first step is to cut it with the water jet. And this is a kind of robust dismantling. Why? It's just because we don't need to care about where is the screw, where is it clamped, or where is it glued, the system. We just need to cut the system at the edge of the frame or at the edge of the housing. And so we can be sure not to damage the cells inside. So this is the easy and robust way, as we say, to open the system. And after this, we take the cells out, and there's a step in between, which we in some cases use. This is the pre-crushing with a shredding system. With this shredding system, we just open the battery cells. We do not crush them down to small pieces. We take just the sieve under the shredding system out, just to cut the battery or the cells into small pieces. They fall down, just cut at one time and not crushed to small pieces. And then we take it to the next step. The next step is the electrohydraulic fragmentation. So we take the cells pre-crushed or not damaged. And you see, in principle, it's very simple. We have a pot filled with water, and the pot itself is the electrode. On the top side, we have some counter electrodes. Here we have 3, but it can be different depending on the system. In our case, we have a reactor system which is in a size of 30 or 40 liters, where we can treat up to 40 cells. It's just on a technical scale. Well, now we are in a process to upscale the whole system. Okay, but in this case, we open the system with a high voltage pulse. This high voltage pulse flows through the water, and the current that occurs make a pressure or a delta pressure about 800 bar, and this is enough to damage the cells, to open the cells and take all these materials out. And the advantage is that we have a kind of very material selective comminution. And after this, we do the skimming and sieving process. As you can see on the left side, it's a slurry of different things. This is the metal, the plastic parts, and also the black mass. On the left side, you see the situation right after the electrohydraulic fragmentation treatment. But on the right side, when you just leave the system for just 1-2 minutes, then you can sieve everything out. You can take the plastics from the top side of the water, and then you sieve the system, and you get these metals, which you can see here on the right side. And then you have 3 fractions. And the next picture shows these 3 fractions. On the left side, again, the metals, which is the foil, the housing, and on the right side, you see the plastic parts, and in the middle, this is the black mass, which can then be treated further. This is not the issue, this is not for today. Today, I just want to talk about the hydromechanical way. After this process, of course, we can try the fractions like metals and plastics and put it over our automated modular sorting line. And when we do so, and we can sort the plastics, for example, with NIR, so near infrared sorting, and we can separate the metals with eddy current, and also the housing with a magnet separator. And when we do so, we have these fractions left. So we have separated all the metal parts, we have separated the plastic parts, and what we have left is the black mass, which we have to treat further. This is just a picture to show you. I don't want to go through this whole picture, but I just want to show that, of course, we are working on the hydrometallurgical way to separate the different metals from the cathode material. And after this, we want to produce new cathode material for new batteries. And as you have seen, we take a lot of water, and the next process step is to clean the water and use it again in the same system. So we want this to use this waste or processed water several times and not to waste this water. So we are at the moment in a process to build up a process line for the treatment of the processed water, and then we can use this several times. So this was a run through my talk. You see, this is the conclusion slide. We have seen the first part of this slide, the disassembly and crushing, the electrode direct fragmentation, and the physical separation of the coarse parts or of the coarse fractions. And after this, the washing and pre-treatment of the black mass. This is the first part, the hydromechanical process step. And but this is the very important step for pre-sorting and for a high selective fragmentation of the batteries to go the next steps. And the better or the more purity we have in this step, the better we can treat it with the hydrometallurgical process step afterwards. So this was it from my side. Thank you very much. And I want to hand over to Andreas Stickler.
Thank you, Jörg, and good afternoon to all of you. I would like to talk about what we do in our department concerning process modeling for the evaluation of sustainability and performance. So historically, we have assisted our research projects along recycling technologies with this environmental life cycle assessment for giving our partners and also our process developers the chance to estimate how sustainable our processes are. But if you zoom out a little bit and have this macroscopic picture of what sustainability and a step further circular economy actually means, you will very quickly understand that environmental burdens like the emission of greenhouse gases and the connected global warming are not the only issues that you have to consider when you want to evaluate sustainability or circular economy. There are thinkers outside that have been defining these terms, sustainability and circular economy. And this is almost philosophic, but we as engineers and scientists, we need to find a way to first assess and evaluate these terms in terms of factual criteria and properties. And then we also need to find a practical way of implementing these. Sustainability needs to reduce the impacts on the environment. So the Ellen MacArthur Foundation, as one of the leading thinkers around this term, even clearly stated that the use of renewable energy sources should be benefited, or should be actually the exclusive criteria for being environmentally sustainable. But there should also be social aspects considered, which has implications, for example, to the supply chains of certain materials. When you talk about specific metals, this is concerned with mining and also the distribution of these materials. But what is also important, and what people tend to forget, is that the economic side is also a major issue or a major criteria for being sustainable. And environmentally friendly. There are some circular economy principles. I've put them down here. So the terms at the bottom bullet: efficiency, sufficiency, effectivity, and obsolescence. These terms, they need to be considered, and they need to be implemented in a new development, in a new technology, and also in a new product.
Technical difficulties at the moment.
Fulfilling all these.
Andreas, are you able to hear me as we've had you cut off? If you want to reload in, Andreas, what I will do is I'd invite Jürgen back on stage, and we actually have a question that was asked for his section. So Jürgen, if you're still here, if you can come back on screen and on the camera, I can ask a question for you.
Yes. Okay, can you hear me?
I can come on screen, but I can't do his talk.
That's okay. Andreas, we'll come back to you in a second. I think it is now working smoothly, but I'll ask a question for Jürgen while we've got him back on, and then let you pick back up where you left off. So Jürgen, we had a question come in for your section. It's quite a long one, so bear with me. So we had a question come in asking, is the supply risk for NdFeB raw material really a long-term risk? If China reduces exports, price will go up and other countries will open mines. However, the opening and establishing of mines will take some time. Can you comment on if risks for different raw materials are short, medium or long-term?
Yes, that's really a problem. Since we are here dealing with basically one major supplier, like I said, there is also another supplier which is in Australia, and there was a major supplier back 15 years ago or 10 years ago also in the US. It is a problem that when prices get unstable, people are looking for new possibilities to get rare earths. It takes a long while to open a mine, to get all the drilling, all the mining declarations you will need. And when prices are different than you started the process, you can face problems. I think it's a long-term risk, especially for heavy rare earth elements. Light rare earth elements, there are also different kind of sources. For instance, in Brazil, you have a very big niobium mine where rare earth is just a byproduct. You can also use this one. However, like dysprosium and terbium, so the heavies you will need to get your device running at high temperatures, these are located in China, also located next to the borders of Myanmar, for instance, and we all see the situation what these countries are currently dealing with, and we just have to be aware that these are the sources where we get the materials from we are dependent on. And in terms of heavy rare earths, I really see a criticality. In terms of light rare earths, the amount which is needed is also dependent on the other kind of products which can come to the market. The foresight study I showed you is rating heavy as well as light rare earths as critical in terms of supply. What I just want to emphasize is another kind of technology which is not on the market yet, which is magnetocaloric cooling, for instance. So if this technology is come to the market, you will have a huge new demand for neodymium iron boron magnet, despite the huge demand for EV mobility. And then you get really an issue. You can then really think about opening some other kind of mines. And I think it's very important for Europe and also for other countries to collaborate, to get there some consortia working, which can helping mines also running. The price, I know the price is always for now. You will have a price of about €100 per kilo, $100 per kilo neodymium at the moment. So if this price will drop, then the mine in Africa, for instance, can be economic, not feasible to be working. So if you have some huge companies collaborating, it can be a deal to mitigate this supply risk, let's say. But I think for heavy rare earths, it's really there also in the near future, and independence of technology, which can come in the next 5 to 10 years, it can be also a problem for light rare earths.
Thank you, Jürgen. And if any other attendees do have questions, I've seen we've had a couple more just come through there, which is great. Please ask these in the Q&A tab, and we'll come to them at the end of the session. Andreas, are you back with us?
I am, hopefully, and I apologize for these technical issues.
It's okay. It's modern technology always likes to throw a spanner in the works. I think your camera may have frozen. For the sake of keeping the audio, I would recommend turning that off. Again, apologies to those at home. But Andreas, back over to you. And if you'd like to recap your slide, as I'm not sure what was missed there.
Yeah.
Thank you very much.
Right. Thank you, Liam. So yeah, when you do process or technology development or any kind of new product design, what you need to keep in mind to really get a sustainable product is a variety of different criteria or aspects. Categorize or summarize in the categories socially, economically, environmentally friendly, or at least with a low negative impact. And circular economy, on the other hand, has some criteria or principles that you need to fulfill in order to reach such a practical implementation. And this is why we do process modeling for evaluation in order to reach that implementation. Circular economy means, in one aspect, to close the loops or to close the process cycles for a product on many different stages. We have seen it in Jürgen's and also in Jörg's talk on magnet recycling and on battery recycling, that there's different opportunities depending on the technologies available and also on the design of the products for a material to re-enter the economy in a circular fashion. But what is the prerequisite here is, on the one hand, you need to give also these rephases here a value creation. So somebody needs to close these gaps to make the loops or the product life cycles circular with new business models that are economically feasible. By the way, also, of course, environmentally and socially feasible. But also, what might be another prerequisite here, following an idea by Thomas Rau, is that you need to have some sort of product responsibility that you owe to your product in order to make it possible to enter a rephase, either reuse, remanufacturing, or recycling. And this is an idea that is new to the industry, is new to the economy, and we build our modeling and evaluation method in order to be able to measure these kind of responsibilities or this kind of impacts that we need to fulfill in order to build circular economy and sustainable products. What we need in order to have a circular economy ready product or technology are three things that have to be fulfilled and accepted along all the product lifecycle and all the process chain. It's consent that we keep a material and keep a product in the cycle. Therefore, we need standards on the materials, on the parts, and also on the business models. And we need an infrastructure that is ready to keep the materials in life and keep also the products and the parts ready for eventually being reused. And that states even more criteria and issues to be fulfilled by new technologies, by new materials. And I've summarized them here. It's not only ecology and the economy, but it's also the criticality, which involves aspects like the supply risk with certain raw materials or functional materials. It's the efficiency of devices. It's eventually the programmability of materials and devices. And if you consider aspects like recycling as being a function, an additional function to a product, then it's for sure also the multifunctionality that needs to be fulfilled by future products and materials. So you see, there's a lot of criteria in these different classes of aspects that need to be kept in mind. And that's why we use this digital process modeling for our own technologies, but also for evaluation of the products of our customers and partners. And this evaluation I've sketched here very quickly essentially summarizes or assesses the criteria that come up from, for example, methods like the life cycle assessments for environmental impacts on multiple levels. And these levels are materials, products or product parts, devices, but also services and the entire process chains that build our economy, or in the ideal case, our circular economy. And then we evaluate the criteria and compare the individual or the alternative materials and the individual process chains in order to find a best compromise between the different criteria. And I very quickly want to show you how we do it, because it's a quite complex task. For many products and for many developments, you need to go to a high detail of process descriptions, and that's why the processes themselves are what we call up our in our bottom-up description, the smallest unit necessary for addressing the problem in question. So in this example here, I have a electrolyzer cell that we might be able to describe in terms of a sustainability assessment via input flows and output flows. And these flows, they carry all the information that is there to describe the process as accurately as possible, but they also carry the information about environmental impacts, about criticality, and any technical risks that might be associated with the flows. In the blue part of the process description here, the process parameters, we put in technical criteria. These technical criteria are as well important because we can then use these parameters in order to make a process or process chain optimization and get physical or engineering insights into the mechanisms inside of the process, but we can also use these parameters to tune or optimize the process in order to make it more efficient with respect to certain criteria. And again, the criteria can be concentration or amount of input and output flows or of certain products that come out of the process, but they can also relate to the impacts that are associated to the flows, like global warming potential or supply risk or economic factors. And our tool then uses the individual process descriptions that are always in the same style to automatically build these process chains. And that allows also then to connect the individual or alternative process chains to circular systems and give back a feedback loop in terms of informational feedback, but also in terms of the impacts and closing the process chains for handing back material to the start of our system boundaries. One word on the information base. Of course, you can imagine there is a high need or a high amount of data and information necessary in order to describe all these input and output flows and process parameters. And that's why we built this method as well, because it's implemented in a way that makes access to the experiments, so to the hardware that we are using, but also to external databases and repositories easy. And this is ongoing work, so we need to find a way to digitally and automated input and output information to these process models in order to keep up with all the properties and all the impact criteria that we need to integrate here in these model systems. And now I want to show you 3 use cases, 3 examples of evaluations that we performed, just to show you how we are able to address these different impact criteria and different materials properties in order to have a holistic picture of the development of the developed technologies, the materials, but also the products or business models. So the first example is the production of hydrogen via water electrolysis, and this was motivated by the EU's hydrogen roadmap, which states that by 2050, the European energy, the final energy demand of the European Union will be delivered for 24% by hydrogen. That means this is way over 2,000 terawatt hours per year, which equals to over 50 megatons of hydrogen necessary to fulfill this goal. With the current technology, that means the integration of over 60,000 electrolyzer devices. Well, compared to what we have at the moment is 300 electrolyzers that produce around 3 megatons per year. This is quite something, and we claim this might be critical for many reasons, but majorly for the catalysts necessary to run these devices. For the catalysts, or for the electrodes of these water electrolyzers, there's platinum, iridium, and cobalt used. And if you consider these numbers, as I showed here, the 60,000 electrolyzers require 25 tons of platinum, 60 tons of iridium, and about 40 tons of cobalt. And everybody knows, so these are critical elements as they are cost efficient, but they are also under high competition with other applications. Cobalt, for instance, is a major ingredient to the active materials in lithium-ion batteries. So there is a competition, and the market for these is under a certain stress. So we had a collaboration with colleagues from the Max Planck Society, and they came up with new synthesis ways and new materials for these electrolyzer catalysts. And I've stated 3 different materials here, or 3 different synthesis pathways, resulting in cobalt oxide that was templated, so synthesized with a commercial silicate, SBA15, a cobalt oxide synthesized along with used coffee, so ground coffee powder, and a nickel oxide that was used with spent tea leaves, also in powder form. And if you follow the synthesis pathways in lab scale and you put them into our model, we are able to evaluate different properties, different impact criteria next to each other. So the geopolitical risk, for instance, in this dark green color here indicates the supply risk and also the geopolitical component of sourcing the main metal in these catalyst materials. But we also have process parameters like the net process time here play a major role. The current density as a property of the resulting material, so an indicator for the catalyst activity at the end. And in light green, the global warming potential, which is one criteria or one indicator for the environmental sustainability of the process. And with our method, you can not only compare different pathways with each other, which we have done here in the left-hand part of the slide, but you can also follow the individual process steps along the synthesis pathway, which we have done on the right-hand side here, and get a good idea of where the impacts are majorly coming from, on which process step has the most impact. A second example is on electromobility battery recycling or remanufacturing, and the questions there were, what is the most profitable alternative at certain stages at the end of life of a vehicle battery? How do you reconfigure, and what is your choice in terms of recycling pathway? So we built a more macroscopic model here. There's not too many details in there compared to the catalyst synthesis model in the first example, but we have categories like our process routes that I summarized here with this color code legend on the left-hand side. So we consider the reuse of the pack itself, so this battery system, reuse of certain components of these, or dismantling the whole system down to the individual modules or cells and then giving them to either pyrometallurgical recycling or hydrometallurgical recycling. And the results are clear. I will not go into the details here, but I can state that in the overall system, we had a value generation of $4,700 per pack, which includes all possible alternatives here, or all alternatives considered, and applying certain approximations. And if you now zoom in and compare different pathways with each other, you will come to the following results. So on the left-hand side, we have considered the reuse of individual lithium modules as a grid supply. And in our estimation, that leads to a very high value generation in terms of economic value of over $2,000 per pack, consistent of 16 modules. And if you compare that to what is nowadays, a major route is the pyrometallurgical recycling. This sums up, if you consider all the individual steps in between, to only a plus of $160 per pack. This is, of course, an estimation, but it gives you a very clear picture of where you can obviously tune and optimize your process routes in terms of closing different loops or more profitable loops for the circular economy of these batteries. And the last example is a follow-up on Jürgen's talk on magnet recycling. We have looked at this in a project about a year ago. So it's a small internal project, but it gives you a good idea of different alternatives of this recycling route that we give. And it allows us to compare our alternative pathways and also have a look at the individual processes that we have in-house here and give them a rationale for optimization. This is how the model system looks with all the details. It is blurry for a reason. There's a lot of information and a lot of data in there. But this is the summary of the results. So we compared 6 different properties in this slide: the cost of the process pathways, density as a material property of the resulting magnet material, the particle size, which plays technically a very important role, the CO2 emissions, the amount of electricity in there, and the oxygen content in our material, which is also critical for its function. And you can see that comparing different pathways, you can very easily compare the different impacts that are caused for the entire pathway in an aggregated way. But you can also follow along pathways the different properties and impacts, and comparing here 2 pathways, one with an addition of a small percentage of primary neodymium hydride in this mixing step here, MM, and you compare it then to a manufacturing of a magnet with only 10% recycled magnet compared to here. You see that the primary magnet material has a far higher green global warming potential caused by the greenhouse gas emissions for the pre-chain of the fresh material compared to using mainly recycled material and only a small percentage of the neodymium hydride powder. There's much more information in these charts, but this, I think, for now is enough to transport the message that we are able and we need to follow different kinds of impact criteria and different kinds of technical properties in order to ensure that a new development, a new material is sustainable and a product or a business model may actually be practical for implementing a circular economy. So with this as my take-home message, I close, and I'm looking forward to your questions later on.
Thank you, Andreas. And I'd like to invite all 3 of the speakers back onto the stage. Hopefully the technical issues are behind us now, and we'll move on to the Q&A section. So if people do have any additional questions, please do post those in the Q&A, and we'll get round to those now. But we have a few initially, so I'll start off with these. I'll open this one up to everyone, but maybe one person in particular will want to take it. We have a question from Alexander Ulp, who asks, what is your estimate about the break-even point in terms of REE material price, US dollars to kilogram, from when the recycling becomes commercially attractive?
I think also in the current stage, it can be already attractive. I also think that the rare earth element price currently is too low. If you check the mining, I think most of the end users won't agree with that, but that's my opinion. However, I think with the current prices, it can be attractive. And since I can also answer the question of Patrick Ulan, who asked in terms of what kind of recycling possibilities are there on an industrial basis, if there are some companies already doing it. In a worldwide perspective, in the US, there is a company doing recycling for permanent magnets. I think also in Asia, in Japan, there are also companies, and nobody really knows what's going on in China. However, in Europe, if you really want to buy nowadays a recycled magnet, it might be hard. However, saying so, there are some startups putting back their know-how now, and they want to produce magnets from recycled material within the next years. So I think it's realistic to get recycled magnets within the year 2023, maybe, if in a, let's say, smaller, somehow smaller scale, and in a larger scale afterwards. These companies are located in Germany, in UK, in Scandinavia, also in France, in Belgium. All companies are targeting to different kinds of recycling technologies. Some of them are also similar. However, therefore, I think now there is a great opportunity if you are using magnets, and you can also be a supplier for these startups, which all will have a huge demand in the next 4 years to get access to recycled magnets. Therefore, I think it's a really great opportunity to start with this disassembly, because all of them will need to have more or less pure disassembled magnets for them. I'm not aware that a company is really using recycled end-of-life material in a product nowadays, also in small scale. They maybe use some scrap they are producing during the production. That can be the case. That is the case, I guess. But if it's not coming back from another company from the market.
Thank you, Jürgen. And I think you've partly answered there, actually, one of the other questions that we've had come in. But maybe you can give a bit more detail if you feel it's needed. We had a question come in that was asking sort of what timeline could you comment or predict for these industries to become established? I think you mentioned there over the next sort of 5 to 10 years.
Yeah, basically in 5 years they will already be here. So there are at least 5 to 6 different kind of companies and startups trying to put magnet recycling on the market in Europe now, all across Europe, basically. The partner we are working with, they want to produce the first flakes within the next year, and also other companies I know, I think they also try to produce at least at the beginning of 2023, in a small scale, of course. However, all of these companies will have a demand for scrap material.
Okay, thank you. And we have another question through, which I think may have been for Jörg, who may be having some difficulties as he's not back on screen, but I'll ask it to the group in case one of you can answer. And this one comes in from Christine Schmidt, and she asks, how do you handle the BMS parts? If that is a question that neither of you can answer, I can ask a different one.
I can answer.
I can comment on it. So, yeah, I can try to comment. So, in most battery systems, the BMS part, or at least there is a central computing unit that is a separate box, and it can be disassembled quite easily. We are looking at this, and we are also of course, looking at disassembling the BMS box or the central computing unit, the central control box on its own. So in order to get to the individual components, but there one attractive question is whether these components can be reused instead of being recycled. Jörg, now that you're back, maybe you can continue.
It seems I'm back. Yeah. So if you can hear me now, so maybe I can answer this question. So you can treat the BMS system if you really have to recycle it and cannot reuse it. Then you can recycle it with a different way. So you don't need this electrohydraulic fragmentation. So we take this part out. It's easy to separate that in our process. Then you can take it out and treat it like in a electro recycling industry. So then it's easy to treat that, but it's a different way to treat it.
Okay, thank you both of you. There is another question. We've actually had two that are very similar that have come through, which I would ask all three of you to comment on. So we've got a question asking, is there any industry action underway to promote design for recycling or design for disassembly requirements for battery packs to help overcome potential issues? And attached to that is a question from another attendee who asked if there's any legislative action across the Europe, US and China to make manufacturers of e-motors change their rotor design to help with disassembly. So I think sort of a two-pronged question there, one about batteries and one about motors in particular.
Yeah. So maybe I can ask you this first question. Yes, there is an effort from some companies, and we are working at the moment together with a company. It's a public project, a public funded project with a company together. This is designed on the system level, not on the cell level, but on the system level. We are now working on this design for recycling.
Okay, thank you. Any further comments from any of you on that section?
I can answer the second question.
Yeah, please do.
So I'm not aware of that there is really a legislative point to go to a design for recycling for electric motors to get the magnets out. However, in Europe, it was funded like in September last year, the European Raw Materials Alliance, ERMA. Here are companies, research institutes collaborating to make better use of permanent magnets in motors, and recycling is also an aspect there. So maybe there will be something growing out of that, which can be transferred to the European Union and the European Council, let's say.
Okay, thank you both of you. So we have had two more questions come in. So we have a question here for you again, Jürgen, from Patrick Uland, who's asked, said at the beginning of your talk that there's currently no company, at least within Europe, which produces recycled NdFeB magnets on an industrial scale. Again, we may have touched on this already, but do you know of any companies that do produce these magnets on a small scale? If you're allowed to comment specific company names, I'm not sure. Or use partially secondary raw materials, or all efforts currently in the research area alone?
Yeah, I tried to cover this one during one of my other answers. Like I said, there are different kinds of startups. I'm not aware that they really produce now already today material. I think they will within the next 2 years. But I can't really comment on them since we are not a part of those. We are a part of a collaboration with a German factory, and there the first flakes will be delivered to the market within the end of next year. But the other startups aiming for, let's say, elemental recycling from oxidized material, but also the magnet-to-magnet recycling by hydrogen, these startups will most likely produce also by the end of next year or the beginning of 2023. So like I said, a lot is going on in this section at the moment.
Thank you very much. We have another question through from Alejandro Alvarez. I think there's a couple of questions in here. So firstly, they asked that you mentioned the cutting of batteries with water jet at the beginning of the process. How is your proposal compatible with different types of battery packs that could arrive at a recycling plant? I'll let you take that part there and then move on to the second part of that question.
Mm-hmm. Okay, yes, the first part. I said that it is a robust kind of dismantling because you just need to get to the rim or to the end of a housing of a battery system. You don't need to see the screws. You don't need to know where the screws, the clamps are, or whatever. You just have to get at the end of the housing and just cut the system. Yeah, this is a kind of robust dismantling. And of course, the next question is about the robotics. If we have an automated recycling process or dismantling process, yes, of course we have. This is what I've shown you now here in the talk is just one way we're going, but we have another kind of way for the disassembly. This is an automated disassembly with robots, robot-assisted disassembly. But as we all know, this is much more difficult than a robust dismantling.
Thank you very much, Jörg. And we have another question through from Simon Swallow. So I will just move on to that one now. So he asks, in manufacturing batteries, there are big contaminant issues to ensure the materials are handled safely. In the slides at the beginning, there seem to be a few precautions in place. Are you able to comment on what these are?
Yes, of course. You have to treat it very carefully, and also the logistics is not easy to handle. This is something you have to handle. You have to come over. The logistics is the first thing. You need a very safe container system to handle the system or to handle the battery systems. And to treat the batteries itself. So now it's made just by hand, yeah. But to do it so and to do it safely, you can do it automated. Then you are safe, or the persons are safe. And this is what we are following. So we try to do it automated or just by a robust dismantling. But this counts for all the steps.
Thank you, Jörg. And I think for the in the interest of time, as we only have a few minutes left now, we have a final question in. So the final question asks, what kind of impact does the chemical composition of cells have on economic feasibility?
Yes, it's very high. So if we really would know which kind of materials are inside the cells, if we could let's say separate them beforehand, before we start recycling process, then it would be much easier. At the moment, we have just a mix of different batteries, and to treat them we have to go down to the elements in our recycling process, and this makes it much more expensive than just to go down to the compound and take the compound and use it again, or reuse of cathode material.
Perfect. Thank you very much. So in the interest of time, as I say, I will begin to wrap up. So firstly, we'd just like to thank the three of you again, Jürgen, Andreas, for a great presentation and for answering those questions there at the end. Thank you to everyone who's tuned in for your engagement. We hope that this has been useful for you all. As a note, I would like to mention that we will be publishing the slides and also the video that we had a technical glitch with earlier on our website tomorrow. Alongside that, if the three of you are happy for me to do so, I'm happy to share some contact information for the three of you. So if anyone does want to be in touch to talk about potential collaboration or projects, they can reach out to you directly following on from today. And with that, this will bring us to the end of Kwame e-mobility days. So all of the sessions from today and also yesterday will be available to view again on the website tomorrow. If you've signed up as an attendee, you'll also have an email in your inbox tomorrow to watch all of the sessions on demand. Also a note that the white paper in collaboration with IHS will be available tomorrow and will also be arriving in your inbox. So thank you again to everyone that's joined us. We look forward to seeing you again in future webinars and at a live show some point in the future. So have a great day, everyone, and thanks again to our speakers.
Thank you, everyone.